Hey everyone, it's Mr. Glover here. We'll start our next set of notes. So yesterday we talked about exponential functions and how to use them to model problems. And one of the specific things we talked about was the compound interest formula. That's the focus of today. We're going to focus on the compound interest formula and some of the different terminology used in terms of compounding periods, so that we can apply this to we can apply exponential functions to financial problems. So remember, when calculating interest, we need to know when the compounding periods are. If it is not stated when the compounding period, it is usually annually. So basically, if I don't say, assume it's annually. We're going to go through all the different options. So annually, frequency means every 12 months. Number of periods a year, 1. Semi-annually means it happens twice a year, so it happens every 6 months, or n equals 2. Quarterly means the year's split up into 4, so it happens every 3 months. N equals 4 this time, because there's 4 a year. Monthly happens every month. It's going to happen 12 times a year. Bi-weekly means it's going to happen every 2 weeks. Which means it's going to happen 26 times a year. And lastly, weekly means it happens every week, which means it can happen 52 times in a year. So this terminology is going to dictate what the variable n is, and we're going to have to make sure we use the right compounding periods when we set up our problems. So find the total value of the investment after the given time. We've got an initial investment of $7,300 at 7% compounding interest, compounded semi-annually for 3 years. So we can list out our variables here. We've got A naught, which is $7,300. We have an interest rate I of 7%, which is 0.07. Compounding periods are semi-annually, which means it's happening twice a year, so n equals 2. And it's happening for 3 years, so t equals 3. So we can now plug this into our formula. A equals A naught times 1 plus I over n to the nt. We can then plug our numbers in. A naught is 7,300 times 1 plus 0.07 over n, which is 2 to the power 2 times 3. This simplifies to 7,300 times 1.035 to the power 6. Or when it's all said and done, we will have a principal of $8,974. Let's try another one. $21,000 at 13.6% compounded quarterly for 4 years. So we've got A equals 21,000 this time, or A naught, sorry, initial investment. 13.6%. If you can find that interest rate, please tell me where, because that's a good rate of return. So 13.6%, which divided by 100 is 0.136. And compounded quarterly, so n happens 4 times a year. For 4 years, t equals 4. So we plug it into our formula. A equals A naught times 1 plus I over n to the nt equals 21,000 times 1 plus 0.136 over 4 to the power 4 times 4. Which is 21,000 times 1.034 to the power 16. When it's all said and done, you will have a future value or a principal of $35,855. And so you can see that the term is important here, but the interest rate is king. The interest rate determines how much money you're going to make off of it. Higher interest rate you have, the less time it's going to take to double your money. All right, let's try a couple more of these. We have 1,240 at 8% compounded annually for 2 years. So A naught is 1,240. Interest rate I is 0.08 compounded annually, so N equals 1, and T equals 2 years. So A equals A naught times 1 plus I over N to the NT. With our numbers, this is $1,240 times 1 plus 0.08 over 2 to the power 2 times 1. Or sorry, what am I doing? N is 1. This equals 1,240 times 1 plus 1.08 to the power 2, which will work out to $1,446.34. And last but not least, $18,000 at 4% compounded biweekly for 4 years. A naught is 18,000. I equals 0.04. Biweekly means we have 26 compounding periods in a year, and T equals 4 years. So A equals A naught times 1 plus I over N to the NT. A naught is 18,000 times 1 plus 0.04 over 26 to the power 26 times 4. This equals 18,000 times 1.00154 to the power 104. And when it's all said and done, you will have a principal or future value of $21,121. So up until this point, we've spent all our time going from one initial investment and calculating the future value of that investment. But you're not always stuck solving for that one variable, and you're not always stuck only using this compound interest formula. I could ask a question where we need to solve for A naught, or maybe we need to solve for T, or maybe we need to solve for I or N. The only trouble here is that solving for exponents right now, it requires a bit of guesswork. But what we're going to do is we're going to take the exponential growth and decay formula, the general one. Remember, it's A equals A naught times 1 plus or minus R to the power T. And we're going to use it in a situation where we've got decay. And we may have to start solving for some different variables. So Cole has a maple tree that he likes to use to tap and make maple syrup. Last year, the tree produced 28 liters of sap. If the tree loses 10% of its production each year, how much will it produce in the 10th year from now? So we've got a bit of information. A naught, the initial amount, is going to be 28 liters. Our change, percent change, is 10%. So R equals minus 10%, which would be negative 0.1. How much will it produce in the 10th year? So T equals 10 years. We can now use this general formula to build the compound, or not compound interest, sorry, the exponential decay formula. So if we use A equals A naught times 1 plus or minus R to the power T, we can put in our numbers. A naught was 28 liters times 1 minus 0.1. That's basically losing 10% to the power 10 for 10 years. This equals 28 times 0.9 to the power 10. So after 10 years, there will only be 9.8 liters of sap coming out of that tree. So that's an example of an exponential decay problem where we have to use the general formula and we have to tailor it to the question. We're going to do the same kind of thing, but now we're not going to solve for the future value. We're going to solve for something else. So in this case, how many years will it be producing less than 3 liters? So this time we are given a fixed final value. We're given A equals 3 liters. All the other variables are the same. We still have A naught is 28. We still have a rate of change of 10%, but we don't know T this time. So we can go use our formula. A equals A naught times 1 plus or minus R to the power T. And if we can plug in what we know, A is going to be 3 equals 28 times 1 minus 0.1 to the power T. We can simplify this a little bit. We can subtract 3 and move it to the other side. But what I'm going to do is just simplify my brackets. So we've got a couple of options here. We can solve this graphically by plotting it, and that's how I'm going to do it, but it's not the only way. The other thing we can do is we can divide 3 by 28, and we can test powers of 0.9 until we get really close. That's the guess and check method. So that way will work, but it's maybe not the most elegant solution. What I'm going to do is I'm going to plot one function as y1. I'm going to plot one function as y2. And I'm going to find the intersection point. So we're going to switch over to Desmos here. One function is going to be 28 to the power 0 or times 0.9 to the t. And I guess we'll just call it x. There's one of our functions. And I suppose I should define it as y equals. The other function is literally y equals 3. That's our goal. So we need to figure out where do these functions intersect. We can zoom out and we'll actually see the taller function. This is the decay of the tree sap. If we go down to this meeting point at 21.2, that's when y equals 3. So 21.2 years is the solution for x. That's how many years we've got to wait. If we go back to this, they intersect at 21.2, so t equals 21.2 years. We can now go back, we can plug this into our formula and double check that it works out to 3, but it will work. We know that this one will work. So you've got options how you want to solve this for now. Soon we're going to learn another technique called the logarithm, which will give you even more options. All right, let's try another decay problem. This time we're doing a half-life problem. Fermium-257 has a half-life of 100 days. How much of a 50-gram sample will be left after 365? So we've got a couple of options here. Remember, there's two versions of this half-life formula. You can use m equals m naught times 0.5 to the power t, or you can use m equals m naught times 0.5 to the power t divided by half-life, which would be 100. I am going to simply leave it as t, and I'm just going to roughly calculate how many half-lives we've got. But we don't have to do it that way. We can use this formula as well. So 365 days divided by 100 gives us 3.65 half-lives. Okay, this is what we're going to use for time. We can now use our formula m equals m naught times 0.5 to the power t. M is what we're trying to find. We have 50 grams to start with, times 0.5 to the power 3.65 half-lives. And after this 365 days, we'll be left with 3.98 grams. For the other question, to estimate how many days it will take for the sample to decrease to 5 grams, we're going to have to solve for our exponent. And now we can use either of these formulas. If we use the first one, we'll be solving for number of half-lives. If we use the second one, we'll be solving for number of days. Just to try it differently, let's use the other formula this time. So we're given the initial amount and we need a final amount of 5 grams. So m equals 5 grams. Use the same formula, m equals m naught times 0.5 to the t over 100. But this time we plug in m and m naught and we solve for t. 5 equals 50 times 0.5 to the power t over 100. And now we can just plug it into our function like this. We can define 5 as y1. We can define this as y2, and we can find the intersection points. So let's go back to Desmos. Our exponential function this time is 50 times 0.5 to the power t over 100. Oh, I should probably call it x. And our other function was 5. That's the desired number of grams at the end. So y equals 5. And if we zoom out, this models the decay, the half-life decay. This is 5. The intersection point right here is 332.2. So if we go back to notability, intersect at x equals 332.2. So t equals 332.2 days. So we're going to try one more kind of function now. These are going to be percentage increase or decrease, and it's going to be about population growth. So the scale factor is the thing we're going to have to be careful about. We're going to use the same basic formula, but I'm going to use P instead of M or A because we're talking about population. But if you don't like changes in letters, if that's confusing for you, just stick with A for every single one of these. It doesn't really matter. So percentage problems may be expressed as a scale factor. So for example, if your population doubles, we could use some formula like P equals P naught times 2 to the power T, if T is the doubling period. So if the population doubles in 15 years, well, P equals P naught times 2, because we're doubling, but since it takes 15 years to double, T over 15 is our exponent. 1 year doesn't quite double it, but 15 years does. Population triples in 7 months. Well, this time the scale factor is 3 because we're tripling. P equals P naught times 3 to the power T over 7. In this case, T equals number of months. Half-life of strontium is 3.6 years. Well, since we're talking about a mass, we can use M equals M naught. It's a half-life problem, so 0.5 is going to be the scale factor to the power T over 3.6. In this case, t equals number of years. So when you're trying to define functions to model exponential growth or exponential decay, the big idea is you need to find the appropriate scale factor. And if you're not sure, you can always just use the rate of change. You can use this, this formula to calculate it. If you're doubling, rate of change is plus 100%. But the big idea is with t. T is going to be the period of time that it takes for the doubling or the halving or the tripling to occur. If you just leave t only as your exponent, then you have to interpret what t means. T is the doubling period. If you divide it by the period of time it takes, like 15 years or 7 months, you just have to remember that t actually means number of years now instead of number of half-lives. So that's where I'm going to end things today. I'm going to send out a worksheet for you to try, compound interest problems. It's basically using the compound interest formula to solve for different variables in different situations. So you might be solving for time in one, you might be solving for initial investment in another. So I'll end the video here. Have yourselves a great rest of the day, and I will see you all tomorrow in our chat. Bye for now.